All right, everyone. Hopefully you are all having a fantastic evening. Um, Go ahead and start working on our study guide here. Um, and hopefully help clear up any kinds of misconceptions that we might have kind of going into it. Um, so kind of first and foremost, taking a look at number one. We're given a situation here where we're being asked to figure out a valid way to model a particular exponential equation. Now, we had a couple of ways that we saw that we could do this. The one that we very first started out with in unit, in 3.1 was this idea that I could model exponential growth and decay with this formula of f of, I'm going to use t just because we use t for like most of what we're doing here. F of t equal to a times 1 plus r to the value of t. This is like our kind of generic, or at very least to some extent, our most generic way that we could represent what was going on. But then we also saw that while this one was kind of good at modeling what's going on with like discrete cases, we also had the ability to model something a little bit more continuous. So for that, we might say that f of t was equal to this a times e to the rt. And we later kind of modified this again, not like that this was super necessary, just to kind of keep with our convention here, that this was a sub 0 e to the rt, or a naught e to the rt. And so what we are looking for here is something that is corroborating kind of these pieces of information. In this case, we are told that an initial population of mice, which starts at 142 mice, is increasing by roughly 13% per year. We're trying to figure out what's going on after 15 years, just kind of setting up the model here, and then we would like figure out what we would plug in afterwards. So in this case, our R value is going to be that 0.13. And so for this model here, we might say either that f of t is equal to that initial 142 times 1 plus that 0.13 to the power of t, or that we had that 142 times e to the 0.13 times t. And we also saw a way kind of a little bit later with the 3.5. So times 42, and we'll look at models like this, where we could take the kind of projected amount of mice that we get. So for instance, if we're increasing by 13% each year, then we could say something along the lines of like, we're going to have 160.46, mostly just for math purposes, mice after 1 year. So 142 e to the r times 1. And then we could solve this for r. And when I do, I'm going to get that r is equal to the ln of 1.13 over 1, which we could also use for that value of r. It's slightly different than using the r equals 0.13, but it's close enough that it'll get the job done. And frankly, both of these interpretations are just as good, and either one would be valid. So not one that we saw really listed here, but this would also have made for a good value of r. All right, taking a look at example 2 here. So we are told that we have a radioactive substance that is decaying at 5.6% per month. And we want to know how much is going to be left of our 120 gram sample after 2 years. In this case, I'm going to go ahead and assume that R value that we're given, this negative 0.056, negative because we are decaying. we'll go ahead and use that for our decay rate. Again, we could use the discrete, we could use the continuous. Both would be totally fine. We could even set up something very similar where maybe we do like our initial amount here of like 120 times 0.944, since that would be like how much is left, and then we can find an R value that way. I think I demonstrated that away in class. But I'm going to go ahead and stick with that 5.6% decay, which gives us the following equation that A of t is equal to 120 times e to the negative 0.056 times t. In this case, we want to know what's going on after 2 years. Because this is a monthly decay rate, the number of months in 2 years is actually going to be 24 months. And so this is going to be 120 times e to the negative 0.056 times 24, which gives us 120 times e to the negative 0.056 times 24. I get 31. How many did I say? Round to 3. I get that this is equal to 31.296 grams. Again, you can use a slightly different value of R. We showed in one of my classes that you get like about 30 grams if you use a slightly different method to find R. I would accept both of those. Those are both great. All right, let's take a look at number 4 here. So in this case, we've got a compounding interest problem. So the question is, how much money is someone going to make if they have an initial value, initial amount of $10,000 that has been left to compound continuously at 6% for 15 years? So we had two different ways, two different formulas, or kind of one formula, but one is like the limit of the other. But that's really neither here nor there. So two different formulas here. We had one that was P times 1 plus R over N to the NT. And then when N is like infinity, which is our continuous case, that turned into what we called the PERT equation. All right, in this case, because we are being asked to use our continuous compounding, we're going to go ahead and use our PERT equation here. So in this case, we've got 10,000. This is A of t equal to 10,000 e to the 0.06 times t. And A of 15, what happens after we plug in 15? So 10,000 times e to the 0.06 times 15, which I get is 1,000 e 6. I get that this is going to be $24,596 and a whopping 3 cents. All right, number 5 is just our definition for logarithms. Be careful of what I've done with the variables, would be my advice for number 5. And then we'll look at a couple of the examples here for number 6. Very, very similar. Again, just simple applying the definition of logarithms. So let's look at 2. Let's look at 4 to the power of x equals 9. Let's look at x to the power of 9 equals 4. So in this case, our definition from logarithms said that if I have x equals b to the power of y, then I can reformat this to say that log base b of x is equal to y. In this case, if we think of base power result, base power result. In this case, for the first one, our base is going to be 4, our exponent is x, and our result is 9. And so this is going to look like log base 4 of 9 is equal to x. Here, our base is going to be x, our exponent 9, and our result is 4. Log, a little bit weird, but base x of 4 is 9. Okay. Now, in tandem with our kind of properties here, when we think about like what it is with logarithms that we are actually trying to solve, ultimately the logarithm is asking the question, what is the power that we have to raise a particular base to in order to match our result? And from that, I mean, from several things, but chiefly from just among that basic definition, we get what is called the identity, or one of the identity property of logarithms, which says that if we have log base b of b to the power of x, what power do I have to raise our base b to in order to match b to the power of x? Well, that is going to be x. So we'll take a look at a couple of these here. Let's take a look at log of negative 10,000. Let's take a look at log base 1/2 of 16. Let's take a look at the ln of e to the 6. Let's take a look at the ln of 1. It's like half of them. Yeah, that should be good. Okay. So first and foremost, what base are we talking about when this is just log? Well, the implication here is base 10. So you might be looking at this and being like, oh, well, 10 to the 4th gets us to 10,000. And red herring here, maybe this would then be -4 because of the negative on the inside. But remember that the negative in our exponent, if I rewrote this and said 10 to the -4th, that negative actually makes us take the reciprocal. So this wouldn't be -10,000. This would be 1 over 10,000. It turns out there are ways to get negative results by doing exponentiation, but the way that we need to do that requires us to use imaginary numbers. We're not going to see any of that, certainly not for a while. Maybe I'll throw in a little bit of stuff towards it, like at the very, very tail end of this course. But for now, there isn't a way to take a positive base, raise it to a power, and get a negative result. And so because of that, there are no solutions here. This simply does not exist. Log of -10,000, it creates a domain error. That would not work. All right. Log base 1/2 of 16. Okay. So what I can do, I know I can get 16 pretty close to 2. So for instance, I could think of this as like log base 1/2 of like 2 to the power of 4. And that's almost the same. We can almost use our property here, but you'll notice that, okay, 2 and 1/2 clearly are not the same. But we're going to use that property that we just mentioned above that I then erased, which is that if I raise to a negative power, that is going to take the reciprocal of what I am looking at. So for instance, I could write this as log base 1/2 of 1/2 to the -4, and that -4 flips me from 1/2 to 2, and then that 4 takes me from 2 to 16, and so log base 1/2 of 1/2 to the -4 is just going to be that -4. Okay, ln of e to the 6th, this one's not too bad. Ln, we know, of course, is our log base e of e to the 6th. What power do I have to raise e to in order for it to equal e to the 6th? That's just 6. And for ln of 1, this one's maybe a little bit tricky. So what power do we have to raise e to in order for it to equal 1? Well, what we can remember is that, and this is going to end up being true for any logarithm, any base of 1, is that e to the power of 0 is equal to 1. That. E to the power of 0 is equal to 1. And so in this case, what power do I have to raise e to in order for it to equal 1? I have to raise it to the power of 0. All right, let's take a look at number 9 here. So this is, we are being asked to expand the ln of x squared times the square root of y over 12yz plus y. So we're going to use here our kind of log properties here. So our product property, log base b of m times n, an inner product turns into outer sum. We have an inner quotient turning into outer subtraction. And we have our power property, which takes an inner exponent and turns it into a coefficient. All right. So let's consider what we have here. Just to make this a little bit cleaner, I'm just going to kind of go one step at a time. There are ways that you can be a little bit more ambitious, but I think doing this a little bit more slowly can be fine, particularly if this is something that you have struggled with. So what I'm going to do here, I'm going to first apply, using this as m and this as n, I'm going to first apply our quotient rule here. So using our quotient rule. So inner division turning into two logarithms that are being subtracted. This is log, well, base e, so ln of x squared times the square root of y minus the ln of 12yz plus y. And what we can observe from our kind of leftmost is, again, we have some multiplication that we can do here to split. Notice here we actually can't use the power rule just yet because the inside of this logarithm is not all being raised to a power. Notice it's the entire inside here being raised to a power. Like, yes, I have this squared, but it's only applying to the x, not the y. Yes, I have this square root, but it's only applying to the y and not this x. And so using our product rule, we'll go ahead and split this apart into the ln of x squared plus the ln of the square root of y, and then using our power rule on both, using our power rule on both, I get 2 times the ln of x plus, remember, square root is really 1/2 times the ln of y, that power being 1/2. Now, if you look at the subtraction bit here, you'll notice that we don't really match the criteria for any of our rules, right? We're not an inner product. We're not an inner quotient. We don't really have any kind of thing that's raising all the powers here. And so if we leave things as they are, there's not really all that much that we can do, or if we have to, if we don't have any like other avenues forward. And really the only avenue forward that we can consider is the possibility of factoring here. What we can notice is that there is, in fact, a greatest common factor of y. I can reformat this particular logarithm to be the ln of y times 12z plus 1. And when I do that, I now have a value of m times a value of n, which before I couldn't get. And so using my product rule here, we're going to get, again, minus. This is going to be the ln of, we're splitting apart y and 12z plus 1. So the ln of y plus, notice I'm going to distribute that minus later, the ln of 12z plus 1. And the ln of 12z plus 1, we're not going to be able to do anything with that. You'll notice that there is not any more like factoring that we can do. That is just going to be as is. And the only thing that, like, this would be a perfectly fine representation, but you could also distribute this negative all the way through. Important to make sure that that negative is applying to everything that that logarithm becomes. And so this becomes the negative ln of y minus the ln of 12z plus 1. And you would not have to do this, but it could be observed that these are like terms and would combine to be the negative 1/2 times the ln of y. Unnecessary, though. This should give you full credit as well. All right. Now, number 10 is doing the opposite. So in this case, we're doing the exact same rules, but we're doing them in reverse. So this is 3/2 times the ln of 4x minus 2/3 times the ln of 3y plus 6 times the ln of z. Now for this, we have a couple of different approaches that we can take. We can choose either to distribute this 3/2 to every single one of these logarithms. That would be totally fine. Or we could save that till the very end and then do a power rule kind of at the very, very end of this problem. Both of those are totally fine. I think a little bit easier is going to be distributing that 3/2, mostly because it's going to take that y coefficient and it's going to simplify it pretty drastically. So when I do that, I get 3/2 times the ln of 4x minus 3/2 times 2/3 is just 1, which is why I did this. And then 3/2 times 6 is 9 times the ln of z. Now, using our rules, you'll notice that in order to use the product and quotient rules, we need to use the power rule first. So we need to bring those coefficients up and turn them into the exponents that they were. So using our power rule, we get the ln of, important here that the entire 4x is being raised to the 3/2. And that it's inside the logarithm. Both of those need to be the case. And then this is plus the ln of z to the 9th. And then, frankly, you can just go 2 at a time if you really want to. I showed that in class. I'm instead going to shortcut this a little bit. What we can kind of observe is that anything that's positive is going to be a factor of the numerator, and anything that's negative is going to be a factor of the denominator. If you are really struggling doing this condensing, do it 2 at a time. That would be my advice. Work from left to right. Just do 2 at a time. It's a lot harder to mess it up if you're doing that. But I am not wanting this video to be too long. And so I'm going to take some shortcuts here. We've got positive, negative, positive. So this will be numerator, denominator, numerator. And they're all going to be multiplied or divided, right? It's inner addition and subtraction outer addition and subtraction turning into a single logarithm where we are multiplying and dividing. And so what this is going to look like, this is going to be the ln of, our numerator is going to be a product of 4x to the 3/2 and z to the 9th, which you totally could clean up, but I'm lazy and I'm not going to, divided by this 3y. So you could totally do it 2 at a time. If you're struggling with it, do it 2 at a time. But if you feel comfortable, if like that's what you got, like just looking at this, then yeah, you're probably good. You probably don't need to do that. All right, I'm gonna skip number 11 here, not because it's not worthwhile, but because I think the method that we use for 12 is one that would also work for number 11. And so if you can do 12, then that's like great. So this is 2 to the x is equal to 7 to the 2 minus x. So we have two strategies when we are trying to solve these equations. We can either try to match the bases, which normally we only do if it's particularly convenient. So like number 11, you can make both of the bases base 2, and that's not too bad. And if we can't match the bases particularly easily, or even if we can, frankly, then we can rewrite as a logarithm. There are other ways to do this. And I have had students who have asked, like, oh, can I be doing it this way? And to them, my answer will be yes, you totally can. That's fine. As long as what you're doing is accurate, I do not care. Let's go ahead and do this one in terms of rewriting as a logarithm. It doesn't matter what we pick as our base as long as we're consistent. I think we did a lot of base 2 in class, so I'll go ahead and do base 7 here, just for fun. So we'll say the base is 7, the exponent is our 2 minus x, and our result is the 2 to the power of x. If that is the case, then by rewriting as a logarithm, I get log base 7 of 2 to the x is equal to 2 minus x. And using our power rule to drop the x down to the front, that x times log base 7 of 2 is equal to 2 minus x. Our general strategy is going to be to get all of the x's on one side, all of the other stuff on the other. So adding x to both sides of my equation, I get x times log base 7 of 2 plus x is equal to 2. And then here, normally we would combine like terms, but unfortunately we don't really have that luxury. And so instead we'll factor an x out to the front. And then divide by this weird constant, but just a constant. Divide by this log base 7 of 2 plus 1 on both sides. And so I get that x is equal to 2 over the log base 7 of 2 plus 1. All right. Number 13 here. So this is the ln of negative 2x squared minus 7x is equal to the ln of x minus 2. Now, our two strategies are very similar. If we can get matching based logarithms on both sides, then just like with our exponentials, where I didn't fully explain this, we didn't quite look at an example like this, but where I can like drop the bases and just set the exponents equal to each other, that's called the 1-to-1 property of exponentials. We can do a very similar thing with logarithms. We also, though, do have the approach that we could try rewriting this as a logarithm. Both of those approaches are perfectly valid. Both of them will give us the correct answer. This one in particular, though, is really set up well to using the 1-to-1 property. And the 1-to-1 property says if this statement is true, then this statement must also be true without the logs. Assuming it doesn't create a contradiction later, which we will investigate. Now, I want you to note, I'm not dividing or canceling the logarithms in any way. This is using a property. It's kind of like how when we go from like x plus 1 to x minus 2 equals 0, that I can then say that x plus 1 equals 0 and that x minus 2 equals 0. It's not like a math step, it's a logic step. In that case, it's the zero product property, right? But in this case, it's our one-to-one property. In this case, we have a quadratic that we need to solve. Our method is going to be to get everything on one side, 0 on the other. I like it when my a value is positive. So I'm going to do 2x squared plus 8x minus 2 is equal to 0. And what we'll find very quickly trying to factor this is that there aren't particularly good ways to factor it. And so we'll go ahead and have to use our quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. We need to not be making mistakes with our quadratic formula. All right, that's like, we can't do that at this stage. All right, so if you don't know it yet, learn it now, because it ain't going away. This is going to be negative 8 plus or minus the square root of 8 squared minus 4 times a times c, all divided by 2 times 2, 2 times a, which is negative 8 plus or minus the square root of 80 all over 4. Negative 4 times negative 2. Notice that this is positive 16. Square root of 80 is really, really close to 9. We can kind of think of this as being almost like 8.9. And the reason why I'm saying that, normally we could just be done there, and that'd be a great representation for our final answer. But in this case, it's really important to make sure that our solutions actually work. So with logarithms, we run into the possibility of domain issues, which we don't run into with our exponential function. So we need to verify, do the values that we got actually satisfy or actually work for this particular log setup? So if I do plus 8.9, then I'm going to get, or if I do plus the square root of 80, I'm using 8.9 as just, if we don't have access to a calculator, then 8.9 is close enough that you can get a gist. But when I do plus, I get the 0.236-ish. And when I do minus, I get the 0, negative 4.236. And the problem with both of these is that when we take them and plug them back in to my original function, we get the negative, the logarithm of a negative value. And so because both of these turn the inside of our logarithms negative, we have to exclude both of them. Here we have no solutions. All right, let's take a look at number let's do we'll do number 15 here. 14 and 15 are pretty similar, but both of them are going to be solvable in about the same way. So in this case, we were told that cesium-137 decays at a rate of about 2.31% per year. And we're trying to figure out how long it's going to take until there's only 1 milligram left of cesium-137. So again, got this A of t equal to a sub 0 e to the RT. And we, again, can use R equals negative 0.0231 as our rate. That would be totally fine. If we're not going to do that, the alternative would be we would need to set up like 400 e to the R times 1 per year, and then we figure out like how much left if we decayed by this negative 0.0231, how much left of our 400 are we going to have, which we can do pretty easily. That's this times this, so we'd have like equal to 390.76. And okay, then we would solve for R, blah, blah, blah. I will leave as an exercise to the reader to confirm that that R value would be the ln of 0.976, or sorry, 0.9769. And you could use either of these R values. These are both good. They give you slightly different answers, but you know, such is life. Ain't that just the way? Since we used the negative 0.056 before, I'll go ahead and use the ln one just for fun. Again, both are fun. So in this case, our equation here, A of t, is equal to 400 times e to the ln of 0.9769 times t. And we want to know when that amount is going to drop down to 1, e to the ln of 0.9769 times t. So dividing both sides by 400, I get that 1 over 400 is equal to e to the ln of 0.9769 times t. And rewriting this as a logarithm, I got the ln of 1 over 400 is equal to ln of 0.9769 times t, solving for t, dividing by. Or if there were a denominator here, you know, multiplying by the reciprocal. 0.9769. So t, I don't exactly recall here. I think this works out to be, well, okay, you know, while we're doing this, might as well. It's going to be like 259. This is of 400 divided by the ln of 0.9769. Okay, yeah, this is about 256 years. And I think if you use this, it works out to be about like 259, although let me confirm that. I can confirm that very quickly. Divided by negative 0.231. Yeah, you get like 259 here. You get like 256 for the one that I used. So relatively close. I know they're slightly off, but good enough. All right, Newton's law of cooling. So the way that we kind of considered Newton's law of cooling was a little bit different than I think how it is traditionally shown. Just because I was trying really hard to stay within the bounds of like every single thing can be solved like this. What we ended up doing for Newton's law of cooling is we said, okay, we do have that kind of like classic definition that like T of T is equal to, you know, T of 0 minus T sub S times e to the RT. This plus T sub S. You know, all of that. But we instead said what is actually decaying here, the thing that is decaying is this difference in temperature. It's this change in our temperature that is actually what's going on. And if I actually subtract T sub S from both sides, I can rewrite this equation to say that the current difference in temperature as a function of time is equal to whatever my initial difference in temperature is times e to the RT, which makes it match very, very, very well with that generic model that we were working with. So there's not even really an extra formula to remember. All we need to remember is that we are working with this temperature gradient rather than our normal. And if we do that, then this is going to solve exactly like what we saw before. In this case, we are told that our initial temperature of our object, so T of 0, is equal to 5,000. And we're told that our surrounding temperature is 5. And so what we're going to find is that that initial temperature difference, that initial temperature gradient, is going to be 4,995. And this is 16 through 18. We'll do, okay, 16. And so we can kind of go ahead and start building up our equation. So A of t, sorry, not A of t. Let's use the things that I've written. Nothing wrong with using A, but just use this. So our difference in temperature is equal to this 4995 times e to the RT. And what we're given is that when we place the knife in this freezer for 3 hours, that it cools down to 500 degrees. Now, the thing to note here is that the T of 3 being 500 implies that the change, the difference in temperature at 3 hours is 495. And so what we'll see is that 495 is equal to, again, difference in temperature is equal to 4995 times e to the r times 3, because it takes 3 hours for that to happen. Solving for r, I get that, so dividing both sides, I get that 495 over 4995 is equal to e to the r times 3. Rewriting as a logarithm and then dividing by 3. We've done this a lot, so skipping a couple of steps here, or condensing a couple of steps, I should say. We get the ln of 495 over 4995 over 3 is equal to this value of r, and that our equation here, if we choose to format it in terms of our delta t, is going to be 4995 times, or times e to the ln of 495 over here. I should give myself a little bit more room here. Well, actually, you know what? We'll just go on to the next page. That'll be perfectly fine because we'll need this formula anyway for the next two. So that our delta t of t is equal to 4995 times e to the ln of 495 over 4995 over 3 times t. For 17, we're being asked to figure out when the knife is going to cool down to 70 degrees. But the thing to note about 70 degrees is that what this actually is a temperature difference of 65 degrees. And so the equation that we get is 65 is equal to 4995 e to the ln of 495 over 4995 over 3, all over 3, times t. Solving for t here, dividing by 4995, I got 65 for 4995 is equal to e to the ln of 495 over 4995 over 3 times t. Rewriting as a logarithm, and then I'm going to go ahead and multiply by the reciprocal as well. Again, condensing some steps here, I get that t should be equal to the ln, sorry, 3 times the ln, multiplied by the reciprocal here, 3 times the ln of 65 over 4995 over the ln of 495 over 4995. Which I think works out, we did it in class. I think Sammy said that this worked out to be like 4.66 hours, which sounds about right. And then number 18 asks what's going on after 24 hours. So our change in temperature is going to be 49.95 times e to the ln 49.95 over 3 times 24, which works out to be 0.00005. Remember, though, that this is our change in temperature. Because we have this positive change in temperature relative to our environmental temperature of 5 degrees, the actual temperature of the object is going to be 5.00005. Very close to environmental temperature. All right, let's take a look at number 19 here. So we're being asked, here's the cumulative part. This is not necessarily all-encompassing, but it should give you a pretty good idea of what we've got going on for our multiple choice section here. In this case, we're being asked to find the average rate of change given the function. F of x is equal to 4x squared minus 2x on the interval x to x plus h. All right. So just a reminder, average rate of change is just a pretentious way to say slope. And our formula for slope is y2 minus y1 over x2 minus x1. The thing that you guys need to recall is that what I have given you here are x values. This is x1, this is x2. So what we need are y1 and y2, which is what we get when we plug x1 and x2 into our function. In this case, plugging x in for f of x does nothing. X squared, 4x squared minus 2x is perfectly good. Plugging x plus h does do a little bit of something. This is 4 times x plus h squared minus 2 times x plus h. Now, normally, I'd be fine not simplifying this. Ultimately, though, because this is multiple choice, it's actually going to be beneficial for us to simplify this. So doing a little Punnett square here for x plus h times x plus h, I get x squared, hx, hx, and h squared, which gives me x squared plus 2hx plus h squared, and then distributing that by 4, I get 4x squared plus 8hx plus 4h squared, and then distributing this negative 2 minus 2x minus 2h. And so y2 minus y1, I get, so n average, this is going to be 4x squared plus 8hx plus 4h squared minus 2x minus 2h minus, make sure we're subtracting all of y1, so that negative is going to distribute, 4x squared plus 2x, because the negative distributes, all divided by x2 minus x1, x plus h minus x. And here we get a lot of simplification. So 4x squared cancel, negative 2x and positive 2x cancel, and the x's in the bottom cancel. We end up with 8hx plus 4h squared minus 2h all divided by h. This h is distributing, and when it does, it's going to cancel here, 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 here. We end up with 8x plus 4h minus 2. Taking a look at number 20, we're asked to find the asymptotes of the function f of x is equal to x squared minus 6x plus 5 over x plus 4. So we can classify our asymptotes into kind of two separate categories. We have the end behavior asymptotes, which are going to be horizontal or slant. And then we have the zero of the denominator asymptotes, which are going to be our vertical asymptotes, or theoretically holes, which we'll want to make sure that we're avoiding. Let's start with end behavior. So in this case, we need to figure out, are we looking for a horizontal asymptote or a slant asymptote, just because our techniques for finding the two are fairly different. And in this case, because the degree on top is bigger than the degree on the bottom, we're going to have a slant asymptote. Actually, specifically because it's a difference of 1. But in all cases where I'm asking for this, that's going to ultimately be what we're looking for. Otherwise, we could get like a quadratic asymptote or like a cubic asymptote or something like that, all of which would be fine, but nothing too crazy here. Just the slant asymptote. And the way we find the slant asymptote is by doing our good old-fashioned long division. So 4 plus x dividing into x squared minus 6x plus 5. So this is going to be x, so matching. So this is x squared plus 4x. Get 0. Negative 6 minus 4x gives us a negative 10x. Then dropping down to plus 5 and matching. And theoretically here you could stop, but it's actually good form to keep going just to make sure that we do end up getting a remainder, which in this case we do. We have a remainder of 45, which is important because that actually implies that this is an asymptote and not like a line, something like that. And so in this case, our slant asymptote is going to be the line y is equal to x minus 10. It's just this part right here. Now, for the zeros of the denominator, in order to figure out if we only have holes, or if we have holes, or if we have vertical asymptotes, we also are going to need to factor the numerator here. In this case, that's not too crazy. Two numbers that multiply to make 5 that add to make negative 6 are going to be negative 5 and negative 1. And what we can note is that there are no factors on top that match the x plus 4 that we have on bottom. That implies asymptote. In particular, the asymptote is going to appear when x plus 4 is equal to 0. And so the vertical asymptote that we get by subtracting 4 from both sides is the line x equals negative 4. Okay, given a function. So this is f of x equals 4x to the 5th minus 8x cubed plus 7x. We were being asked, is this function even, odd, both, or neither? It's never going to be both. The only function that would be both is f of x equals 0. This one is both. But it's the only function that's both. So cool that it exists. We're not going to ever see it. Not a particularly interesting function beyond that property. Plenty of functions can be neither. That's totally possible. If we are curious, if we're unsure, what we need to do is our definition requires that we plug in negative x and we see what's going on. And that's totally fine. If the negative doesn't get removed from each of our terms, if it doesn't like if we don't square the negative to get rid of it, then that component points to being odd. But here we can shortcut because we're looking at a polynomial. All of our odd all of our odd powers are going to let the negative kind of pass through, and all of the even powers would like erase the negative. And so, because in this case all of our powers are odd, remember that there's this implied power of 1 here on the x. So the fact that all powers here are odd, all powers being odd, does point to the fact that this is going to be an odd function. Now, it's really important that it is given in this form. I have thrown some tricky ones. Remember that like the x plus 2 squared, like because of that squared, it really felt like they were all going to be odd. But when you do out the Punnett square, you get like x squared plus 4x plus 4. And then it's a mix. These two act even, and this one acts odd. Looks like it's going to be even, I should say. I think I said odd there. But in this case, because they are in that standard form polynomial and because every single exponent is odd, we are good to assume that they are in fact odd. And again, the way we would confirm that, notice that when we plug in negative x, the negative when raised to the 5th makes it pass through. The negative when raised to the 3rd makes it pass through. And the negative when raised to the 1st makes it pass through. And the fact that this function is the negative version of the function that we started with means that this is an odd function. All right, final question here. Oh, this is a good one. We are being asked to solve the equation 2x squared plus 5x plus 7 equals 0. No numbers that multiply to make 14, that add to make 5, and so we are going to have to use the quadratic formula here. This is negative 5 plus or minus the square root of 5 squared minus 4 times a times c, all divided by 2a. Okay. This here is going to be 25 minus 56, which is negative 31. So this is negative 5 plus or minus the square root of negative 31 over 4. And negative 31, 31's a prime number. This is going to be I root 31 over 4. And we could, if we wanted to be like, doing the good job of separating this out, negative 5 over 4 plus or minus I root 31. All right, hopefully that was helpful. If you guys do have any other questions, I've already had a couple of people shoot me emails. Please feel free to continue to do that. But beyond that, I hope you all have a fantastic rest of your night, and I hope you guys come into tomorrow feeling good and confident. Take care, you guys. I will see you all tomorrow.